Hi, Assalamualaikum. Welcome back to my channel, Physics from 5 KSSM. Today, I want to discuss 3.3 Electromotive Force, EMF, and Internal Resistance, Part 1. In this video, I will discuss 3 learning standards. The first one, define electromotive force E, explain internal resistance R, conduct an experiment to determine EMF and internal resistance in a dry cell. What is electromotive force? There are various sources of electromotive force, EMF, like electric generators, dynamos, batteries, and accumulators. Or we can say voltage source. The electromotive force EMF, E, is the energy transferred or work done by an electrical source to move 1 coulomb of charge in a complete circuit. I hope you still remember the potential difference formula, V equals to E divided by Q. By referring to the same formula, EMF can be defined as, using this formula, E divided by Q. E is energy transferred, Q is amount of charge flowing. Thus, EMF is equals to work done by an electrical source, E, per unit charge in a complete circuit, meaning from positive terminal to negative terminal. The SI unit for EMF is also volt or joule per coulomb based on the formula here. So you can see the picture here. This is a lead acid accumulator, and this is dry cell or battery, alkaline cell, or we have lithium ion battery. This one, the different material used as electrodes or electrolytes. Okay, let's look at, this is a one battery, label 1.5 volt. What does the label means? The label actually shows EMF of a dry cell is 1.5 volt. This also explains that the dry cell can supply 1.5 joule of electrical energy for each coulomb of charge in a complete circuit. So electrical energy used is 1.5 joule per unit coulomb. So this label represents EMF of a dry cell. Electromotive force and potential difference have the same SI units. However, electromotive force differs from potential difference under different circumstances. So we will discuss later the difference between EMF and potential difference. Let's refer to activity 3.6. Aim to compare between EMF and potential difference. Apparatus required 1.5 volt dry cell, cell holder, switch, bulb, connecting wires, and voltmeter. You can look at this arrangement of apparatus. So we have this one is a bulb, this is a dry cell, switch, a voltmeter connected parallel or across the battery. When the switch is open, we call it open circuit because there is no current flow in the circuit. The circuit is broken. Observe what happens to the bulb and record the voltmeter reading. And then close the switch. We call it closed circuit. Now current can flow in the circuit. Observe what happens to the bulb and record the voltmeter reading. Let's look at sample of answer here. For open circuit, the circuit is broken, no current flow, the bulb does not light up. The voltmeter reading shown on the scale as 1.5 volt. For closed circuit, when the switch is closed, the bulb of course light up. What happens to the voltmeter reading? The voltmeter reading becomes 1.3 volt. So can you see the difference between the readings here? So what caused the difference in the reading here? Let's discuss some questions under this activity. What is the change in energy when the bulb lights up? Electrical energy to light energy and heat energy. 2. Based on the result of this activity, which circuit measured potential difference across the bulb? Closed circuit. What is the quantity of electrical energy released by the bulb for every coulomb of charge that flows through it? The value of electrical energy per unit charge is 1.3 volt. The amount or quantity of electrical energy for every coulomb of charge is 1.3 joule. What is EMF of dry cell? EMF equals to 1.5 volt. What is the quantity of electrical energy supplied to every coulomb of charge flowing through the dry cell? 1.5 joule, because 1.5 volt means 1.5 joule per coulomb. What is the difference in voltmeter readings between open circuit and closed circuit? Discuss why this difference occurs. Okay, the difference in the voltmeter reading, you can see the first in the open circuit, the reading is 1.5 volt. In the closed circuit, it becomes 1.3 volt. So for the open circuit, no current flow or no voltage drop. Thus, the reading of the voltmeter is equals to EMF of the battery. For the closed circuit, current flows. So the current flow and produce voltage drop. The reading of voltmeter becomes less than EMF. So for the closed circuit, there is a voltage drop, meaning some of the electrical energy already lost as heat energy to overcome resistance of the battery, or we call it internal resistance of the battery. Let's look at the difference between EMF and potential difference. Okay, we refer to the same circuit. Okay, for the first part here, we can see the switch is open. No current flows in the circuit. The voltmeter reading in an open circuit is EMF. Meaning the voltmeter here just measure potential difference across the battery. Okay, means the total electrical energy per unit coulomb supplied by the battery. Okay, so that's why we call it EMF. Work done by an electrical source to move 1 coulomb of charge in a complete circuit. If measure across the battery means between positive terminal and negative terminal, so that one we call it total voltage supplied by the battery, or EMF of the battery. So this second part, now the switch is closed, the bulb lights out. In this case, we call it closed circuit. The current flows in the circuit. The voltmeter reading in a closed circuit is potential difference across the bulb V. Okay, let's look at carefully. This part, also known as external circuit. We have only one resistance that we call it external resistance. So when the switch is closed, there is work done to overcome external resistance, meaning there is a voltage across the bulb here. Voltage across the bulb is equals to voltage across 2 points from this point to this point. So you can see the bulb is connected to this point. This side connected to this point. So the voltmeter reading, if we have voltmeter across the bulb, so the reading of the voltmeter is equals to potential difference across these 2 points. So you can see these 2 points also connect directly to positive terminal and negative terminal. Thus, the reading of voltmeter across the bulb is equals to reading of the voltmeter across the battery when the switch is closed. Okay, so the voltmeter reading in a closed circuit is potential difference across the bulb. Let's say if you put one more voltmeter here to measure voltage across the bulb, you will find that the reading of the voltmeter here is equals to reading of the voltmeter here. Okay, so work done to move 1 coulomb of charge between 2 points. So that's the difference. EMF is complete circuit. But if you talk about potential difference, it refers to potential difference between 2 points in an electric circuit. Okay, let's discuss internal resistance. Just now we have carried out the activity 3.6 that shows there is a voltage drop. Okay, when the switch is open and then when the switch is closed, you can see the reading of the voltmeter decrease. So we call it voltage drop. What causes voltage drop in the dry cell? So let's look at activity 3.7 to study the effect of internal resistance on voltage drop. If you use a dry cell for a longer time or longer period, you will find that the body of the battery will become a bit hot, meaning there is heat energy produced when the current flowing through the battery. The wasted energy that we call heat energy is caused by work done to overcome internal resistance of the battery. Okay, let's discuss more on this topic. Okay, activity 3.7 aim to study effect of internal resistance on voltage drop. Apparatus 1.5 volt dry cell from two different brands, brand A and brand B, cell holder, switch, bulb with holder, connecting wires, ammeter and voltmeter. Two different brands means they are using different material for electrodes. Okay, this is for brand A and brand B. So what we do, we connect in this circuit. First of all, let the switch open, record the voltmeter reading, okay, for brand A, and then close the switch and again record the voltmeter reading for brand A. Now you replace the battery A with brand B. Repeat the same step, open the switch, record the reading of the voltmeter, 1.5 volt, and then close the switch, record the reading of voltmeter, 1.3 volt. From the readings that we get for brand A and brand B, calculate voltage drop by using this formula. Voltage drop is the reading of the voltmeter when switch open minus the reading of voltmeter when switch closed. The voltage drop is I times small r. The small r represents internal resistance of the battery. I is the total current flow in the circuit. So using the formula V equals IR, so the work done to overcome internal resistance is I times small r. So the voltage drop equals to work done to overcome internal resistance. Okay. So from here we calculate the voltage drop. 1.5 minus 1.4, 0.1. And brand B, 1.5 minus 1.3. So what caused the difference in the reading? Okay. Y for brand B shows larger voltage drop compared to brand A. Let's discuss some questions under this activity. Why should new dry cell be used in this activity? New dry cells have to be used to ensure that EMF is the same, that is 1.5 volt. Which brand of dry cell experiences greater voltage drop? Brand B just now, 0.2 volt compared to 0.1 for brand A. Why is there difference in voltage drop between the two dry cells? Explain. The battery brand B experiences greater voltage drop because the internal resistance of the battery is higher, meaning require more electrical energy to convert to heat energy whenever current flow to overcome internal resistance, which is higher. Okay, so internal resistance of the battery, we use the symbol small r, is the resistance caused by electrolytes in the dry cell or electrodes. The SI unit for internal resistance R is ohm. Internal resistance causes loss of energy in form of heat in dry cell as work has to be done to move 1 coulomb of charge against the resistance within the dry cell. Meaning to overcome the internal resistance, sum of energy lost as heat energy. The potential difference across the dry cell terminals to be less than EMF when current flows in complete circuit. That's why we can see the reading of the voltmeter becomes smaller than EMF. Okay, let's look at the formula. Voltage drop I times small r equals to EMF minus V. Okay, just rearrange, so we get V equals to negative IR plus E. I hope you know all the symbols here. Okay, this symbol is for electromotive force, EMF. V, potential difference across rheostat. I, current. R, internal resistance. Capital R, external resistance. Okay, so from here we can just rearrange the formula. Thus we get EMF equals to V plus I small r. If you look at carefully, okay, this equation explains that the total voltage supply, some used to overcome external resistance, some of it used to overcome internal resistance. So we get this formula, V equals to IR, we substitute here, factorize I, so EMF equals to I bracket R plus small r. Okay, by comparing the formula with formula V equals to IR, you can see clearly that the external resistor and internal resistance in the circuit actually are in series connection, where I is the total current and this one EMF is the total voltage supplied by the battery. Okay, let's look at experiment 3.5 to determine EMF and internal resistance of dry cell. Apparatus required: 1.5 volt dry cell, cell holder, switch, connecting wires, ammeter, voltmeter, and rheostat. Arrangement: rheostat, this is external resistor 20 ohm, switch, ammeter, 2 dry cell, and voltmeter connect across the battery. Okay, the switch is closed. Rheostat adjusted so that ammeter give reading of 0.2 ampere. Reading of voltmeter is taken and recorded. The rheostat is adjusted again to obtain current I 0.3, 0.4, 0.5, 0.6 and 0.7 ampere. The corresponding readings of voltmeter are taken and recorded. Okay, so we need to have 5 sets of data. The data collected are tabulated and graph of potential difference V against current is plotted. Using the graph plotted, the electromotive force and internal resistance of the cell is calculated. Okay, let's look at the graph. So this is the table of data. From here we can see there are 6 sets of data. Plot the graph of V against I. So this is a sample of graph that you can get. Okay, you can see V is decreases linearly with I. Okay, when we talk about relationship between V and I, V decreases linearly with I. Okay, number 1, based on the graph plotted, perform data analysis. A, calculate gradient of the graph. Draw triangle below the line of graph and calculate. So you will get gradient equals to negative, okay, 1.24 minus 0.84, divide 0.62 minus 0.22. So we get negative 1.0 volt ampere to the power negative 1 equals to negative 1 ohm. Write a linear equation of the graph to relate it to the voltage drop. Okay, the formula used, we can compare it to the linear equation y equals to mx plus c. Based on this graph, y is V, x is I. Okay, now we can have this relationship. The gradient actually equals to negative R. The intercept y equals to EMF. Okay, because in this case the y-axis is V, x-axis is I, so the gradient is negative R and C is E or EMF. Okay, so means from this graph we can determine EMF just by extrapolating the graph until intercept at V-axis and read the value here, 1.5 volt. Okay, to determine the internal resistance, you just calculate the gradient. Okay, calculate internal resistance. R equals to negative gradient. So negative 1 become 1 ohm. So we get from here the gradient. Okay, determine EMF. by extrapolation, so we get EMF equals to y-intercept equals to 1.5 volt. Thus the conclusion, for the graph of V against I, the gradient equals to negative internal resistance, or R equals to negative gradient of the graph, and then EMF equals to intercept at V-axis, or y-intercept. Okay, so this question can come out in the problem solving, okay, to calculate the value of internal resistance and determine the value of EMF. Okay, so this is the conclusion that we get just now, the same thing. So intercept at vertical axis, C equals to EMF, gradient equals to negative internal resistance. Okay, so activity 3.8, to study effects of connecting dry cell in series and parallel arrangement. So we have EMF E, potential difference V, internal resistance R, current flows in the circuit. So we have 6 1.5 volt dry cell, cell holder, switch, connecting wires, ammeter, voltmeter, and off resistor. So we have this circuit. First one, 2 batteries connected in series. The second circuit, we have 4 batteries above here, series, and then there is a parallel part. Okay, result of this experiment, for dry cell in series, potential difference V equals to 2.7. Okay, current I equals to 0.5 ampere. For dry cell in parallel, potential difference 2.9. Current I 0.6. Let's look at EMF. Why the value of EMF for the first circuit 3 volt when the dry cells in series? When dry cell in parallel, we use 4 dry cells, but the reading is still the same, 3 ohm. So this is something to do with the arrangement. Okay, now look at effective internal resistance. Using the formula of voltage drop, IR equals to E minus V. So we calculate the internal resistance for the whole circuit, or for the whole dry cell in the circuit. 2 batteries. So we have substitute here, IR equals to EMF minus V. So we get R here is 0.6 ohm. For the parallel part, okay, current 0.6, EMF 3, V 2.9. So we get R equals to 0.17 ohm. So you look carefully here, the effective resistance when dry cells in series is 0.6 ohm. When dry cells in parallel, the total effective resistance for internal resistance is 0.17 ohm. So the arrangement affect the effective resistance of the battery. Okay, for series one, the value of R become larger. For parallel one, the effective resistance for R is smaller. That's the reason why you can see the current for this circuit is larger than this one. Okay, so which arrangement of dry cell produces smaller effective resistance? Explain. The arrangement of the dry cell in series increases effective internal resistance, while arrangement of dry cell in parallel reduces effective internal resistance. So you can see the difference when the dry cell connected in series and parallel. So this is series arrangement, this is parallel arrangement. For series arrangement, the effective internal resistance is 4R, meaning R plus R plus R. So it becomes 4R. So what happens to the voltage or EMF is E plus E plus E plus E, or equals to 4E. So the total EMF increases. Okay. For dry cell in parallel, effective resistance become R over 4 using the formula for parallel effective resistance. And then the EMF equals to E. So the total effective is smaller. Okay, so if you want to increase voltage, so you need to connect it in series, not in parallel. That's all my video today. I will continue electromotive force, EMF and internal resistance part 2 in my next video. Thank you for watching. Bye.